Hello guys! Welcome to the first ever episode of #Learn with Rhea. And for today's episode, we will learn all together how to solve exact differential equations. Without further ado, let's start. A differential equation of type m as a function of x and y dx plus n as a function of x and y dy equals to 0 is called an exact differential equation if there exists a function of two variables, u as a function of x and y, with continuous partial derivatives such that du of x and y is equals to m as a function of x and y dx plus n as a function of x and y dy. For us to be able to know that the given differential equation is exact, we must first test for its exactness. Using the formula, partial derivative of m in terms of y is equal to partial derivative of n in terms of x. If it is equal, then it is an exact differential equation. If it is not an exact differential equation. After solving for the test of exactness of a given differential equation, we now use the formula partial derivative of f in terms of y equals to m as a function of x and y, and partial derivative of f in terms of x equals n as a function of x and y to solve for the exact differential equation. Let's try these examples. So example number 1, we have 3x squared y minus 6x dx plus x cubed plus 2y dy equals 0. So this is our m and this is our n. First thing to do is to test for its exactness using the formula partial derivative of m in terms of y equals to partial derivative of n in terms of x. So partial derivative of m in terms of y equals our m, which is 3x squared y minus 6x. So since we are differentiating in terms of y, we will treat other variables aside from y as constant. So 3x squared will remain 3x squared, y would be 1, and 6x will become 0. So our partial derivative of m in terms of y is equals to 3x squared. On the other side, we have partial derivative of n in terms of x is equals to our n, which is x cubed plus 2y. So here we are differentiating in terms of x, so we will treat other variables aside from x as constant. So x cubed will become 3x squared, and 2y is 0. So it is also 3x squared. Since these two have the same answer, we can conclude that this is an exact DE. So next thing to do is to use the formula partial derivative of f in terms of x equals m as a function of x and y to solve for the solution for the exact differential equation. So it is equals our m is 3x squared y minus 6x. So we will cross multiply. This will become partial derivative of f equals 3x squared y minus 6x. Then we will integrate both sides. So this will become f. Then we will distribute the integral sign. So become integration of 3x squared y dx minus integration of 6x dx. Since we're integrating in terms of x, we will treat other variables aside from x as constant. So we can put the constant outside the integral sign. So f is equals to 3y integration of x squared dx minus 6 integration of x dx. So we will now integrate. So 3y integration of x squared is x cubed over 3 minus 6 integration of x is x squared over 2 plus q of y. 3 will be cancelled and 6 divided by 2 is 3. So the answer is x cubed y minus 3x squared plus q of y. So this is our first solution for our differential equation. For the other part, we still use the formula partial derivative of f. Now, this is in terms of y equals n as a function of x and y. So partial derivative of f in terms of y equals our n is x cubed plus 2y. We will then cross multiply. Partial derivative of f is equals to x cubed plus 2y partial derivative of y, or simply dy. We will then integrate, so become f. We will distribute the integral sign here. Integration of x cubed dy plus integration of 2y dy. Since we are integrating in terms of y, we will treat other variables aside from y as constant. So we will put the constant outside the integral sign. So x cubed integration of dy plus 2 integration of y dy. So simplify. X cubed integration of dy is simply y plus 2 integration of y is y squared over 2 plus r of x. So our answer is x cubed y plus y squared, because 2 can be cancelled, plus r of x. We will then equate our two solutions. So for our first f, we have x cubed y minus 3x squared plus q of y equals to our second f, we have x cubed y plus y squared plus r of x. So we can see that x cubed y can be cancelled and there is nothing more. So q of y is purely in terms of y, and we can see on the other side that this one is purely in terms of y. So we can conclude that our q of y is this, so y squared. And the value of our r of x is this one, since this is purely in terms of x. So we will now then substitute it respectively. So for our first f, we have x cubed y minus 3x squared plus our q of y, which is y squared, equals to f, or c is okay because it is our general constant. Or the other f, we have x cubed y plus y squared, r of x, which is 3x squared, equals c. So this is our answer. Next example, we have y squared cosine x minus 3x squared y minus 2x dx plus 2y sine x minus x cubed plus ln y dy equals 0. So this would be our m, and this would be our n. So first thing to do is to test for its exactness using the formula partial derivative of m in terms of y equals our m. We have y squared cosine x minus 3x squared y minus 2x. So since we are differentiating in terms of y, we will treat other variables aside from y as constant. Y squared will become 2y, cosine x will remain cosine x, and 3x squared will remain 3x squared, since y, when we derive y, will become 1, so 3x squared times 1 is only 3x squared, and the 2x will become 0. So the partial derivative of m in terms of y is equals to 2y cosine x minus 3x squared. Equals our n, which is 2y sine x minus x cubed plus ln y. So we will differentiate it in terms of x. So we will treat other variables aside from x as constant. So 2y will remain 2y. The derivative of sine x is cosine x. And x cubed will be 3x squared and ln y will become 0. So our partial derivative of n in terms of x is 2y cosine x minus 3x squared. So since these two have the same answer, so we can conclude that this is an exact DE. Next, we will use the formula partial derivative of f in terms of x equals to m as a function of x and y to find the solution for the exact differential equation. So partial derivative of f in terms of x is equals to our m, which is y squared cosine x minus 3x squared y minus 2x. So we will cross multiply. We have partial derivative of f equals to y squared cosine x minus 3x squared y minus 2x dx, or partial derivative of f. We'll then integrate. So this will become an f, and we will distribute the integral sign on this side. So integration of y squared cosine x dx minus integration of 3x squared y dx minus minus integration of 2x dx. Since we're integrating in terms of x, we will treat other variables aside from x as constant. So we will put the constant outside the integral sign. So this will become y squared integration of cosine x dx minus 3y integration of x squared dx minus 2 integration of x dx. So integrate, we have y squared. Integration of cosine x is sine x minus 3y integration of x squared is x cubed over 3 minus 2 integration of x squared over 2 plus q of y. Simplify, we have y squared sine x minus, the 3 will be cancelled, so we have x cubed y minus 2 will be cancelled also, x squared plus q of y. So this is our first solution. So for the other formula, we have partial derivative of f in terms of y equals 2y sine x minus x cubed plus ln of y. So we'll then cross multiply. We have partial derivative of f is equals to 2y sine x minus x cubed plus ln of y dy. We will integrate. So this will become f, and we will distribute the integral sign here. So integration of 2y sine x minus integration of x cubed, dy plus integration of ln y dy. Then, since we are integrating in terms of y, we will treat other variables aside from y as constant. So we will put the constant outside the integral sign. It will become 2 sine x integration of y dy minus x cubed integration of dy plus integration of ln y dy. This two is easy to integrate, and this one is yet complicated, so we will do the integration by parts. So we have, for this, we have u is equals to ln y, du is equals to 1 over y, dv is equals to dy, and v is equals to y. And we will arrange this in the form uv minus the integration of v du. So it will become then 2 sine x integration of y is y squared over 2 minus x cubed. Integration of dy is y plus, this form we have y ln of y minus integration of y times 1 over y dy. So we will simplify. It will become y squared, because 2 can be cancelled, sine x minus x cubed y plus y ln of y minus y plus r of x. So this is our second solution. Now we will then equate our two solutions. For our first solution, we have y squared sine x minus x cubed y minus x squared plus q of y is equals to our second f. We have y squared sine x minus x cubed y plus y ln of y plus r of x. So we can see that y squared sine x can be cancelled, as well as the negative x cubed y, and there's nothing more. So we will have then our value of q of y, which is this one, because it is purely in terms of y. So y ln of y, and our r of x is this one, because the same, it is purely in terms of x, negative x squared. Since we have the value of our q of y and our r of x, we will now then substitute respectively. So for our first solution, we have y squared sine x minus x cubed y minus x squared plus the q of y, which is y ln of y. I forgot. Minus y equals to c. Or we can have the other one, which is y squared sine x minus x cubed y plus y ln of y minus y plus our r of x, which is negative x squared, equals c. So this is our answer for the given exact differential equation.